In this lesson, we consider the topic of nucleophiles. An SN2 reaction requires a very good nucleophile. So what does that mean? Well, recall that a nucleophile is another word for a Lewis base, and that any molecule or ion capable of acting as a Lewis base is also capable of acting as a Bronsted base. For Bronsted bases, it's possible to precisely quantify the base strength. Look up the pKa of the conjugate acid. The weaker the conjugate acid, the stronger the base. Unfortunately, there is not a similar quantitative scale for nucleophilicity. And as we will see in a minute, just because something's a stronger Bronsted base does not actually make it a better nucleophile. In fact, in many cases, it makes it a worse nucleophile. But what I'm going to look at now with you are the principles involved in what makes things a good nucleophile. And based on these principles, on the next slide, we're going to assign grades to a number of the common nucleophiles that you'll see showing up in an organic chemistry course. Okay, so let's get to work with the principles. Number one, definition of a nucleophile. All nucleophiles must have at least one lone pair. If something doesn't have a lone pair, it's not a nucleophile. Secondly, the best nucleophiles will have a negative charge. Why is that? What is a nucleophile? Something that has electrons to share. If it has a negative charge, it has more electrons in it than it is really happy dealing with. I mean, some things are okay with a negative charge because they're weak bases, but they still have those electrons available to share. 3, less electronegative atoms will be better nucleophiles. Again, it's about sharing, right? The more electronegative an atom you have, the more it wants to hold onto those electrons and not share them with another partner, which is necessary for the nucleophile in a substitution reaction. 4th, within a column of the periodic table, the larger elements will be better nucleophiles than the elements directly above them. This one is a little less intuitive and a little less obvious to see. But it has to do with a concept known as polarizability of the electron cloud. If you have something like a bromine, for example, which is down in the 3rd row of the halogens, it's got a big electron cloud, but big electron clouds are a little more squishier, okay? Like a soft ball, a ball that you can squeeze in your hands. Whereas smaller electron clouds on a chlorine or a fluorine are harder. Okay, the electrons around a fluorine are more like a golf ball. The electrons around a chlorine are more like a tennis ball. Okay, it's a lot harder to get them to squeeze. Now, if you think about the mechanism of an SN2 reaction especially, some of those electrons have to be able to squeeze into a very small space. And if that electron cloud is squeezable enough, it can get them in there. Okay, so that's the principle at work here. And then the final principle that I alluded to earlier is that since nucleophiles can also act as Bronsted bases, the better nucleophiles are weaker Bronsted bases. Okay, it is a true fact that Bronsted acid-base reactions that are favorable are faster than any other organic reaction. We will see this fact come up again and again. So if something can act as a Bronsted base and it's going to undergo a reaction that is favorable with a Bronsted acid, it's going to do that faster than it can act as a nucleophile. So generally, the strong bases, there are many more Bronsted acid bases reactions that are favorable when a strong base is present, so it's harder to get them to slow down, smell the roses, and act as a nucleophile. And we will see later on in this unit what happens when an alkyl halide reacts with something that is acts as a strong Bronsted base. Okay, time for the report card. What nucleophiles get an A? Here's our list. Br minus, I minus. They are big, they are weak bases. Sh minus and Sr minus. Again, sulfur being in the 2nd row of the periodic table below oxygen, those electrons are a little more polarizable, and SH minus and SR minus are also weaker bases than OH minus and OR minus. Then this organic structure with a minus charge on carbon, you may think anything with a minus charge on carbon is going to be a really strong base. But if you think about the principles of resonance stabilization of anions, that lone pair, that minus charge, is very resonance stabilized because it can be delocalized onto both carbonyl oxygens. You all met the enolate anion in the unit on acid base, and now this is what I call personally a superenolate, because that minus charge can be delocalized on not one, but two carbonyl groups. Then you have phosphines. These are the only neutral species that get an A, but again, because phosphorus is a second row element and not a first row element, it's a little larger and therefore more of a nucleophile than a base. And then another example with a carbon is cyanide, Cn minus. Its conjugate acid is HCN, which has a pKa of about 9. So it's also not a terribly strong base. The B nucleophiles are all worse than the A nucleophiles in one of these categories, and I have these organized the same way on the chart. Cl minus is more electronegative. It is slightly stronger a base, but that's not actually the factor here. It is more electronegative than Br minus and I minus, so it's less likely to want to share its electrons. OH minus and OR minus, first of all, oxygen is more electronegative than sulfur is, but second of all, these are both much stronger bases. The pKa of H2O, which is the conjugate acid of OH minus, is 16, and the pKa of alcohols, which are the conjugate acids of OR minus, are also 16. Once you're getting into things as bases as strong as hydroxide, they're strong bases and they're going to want to act as bases. The next one that's going to get a B is the regular enolate as opposed to a superenolate. We have a minus charge on carbon, which is not as electronegative as oxygen, so it's better in that regard. But this is getting into being a fairly strong base. The pKa of its conjugate acid acetone is 19.2. I might give this one a B plus because enolates are actually very good nucleophiles towards SN2 reactions, but I can't quite push it over the top and give it an A because it is such a strong base. And then another case in which you have a carbon-based nucleophile is what we call the alkyne anion, the conjugate base of acetylene, an alkyne. And its conjugate acid has a pKa of 25. So this is another case in which we have a carbon that's nucleophilic, and the nucleophilic carbons are really, really important in this course because those are the nucleophiles that will be used to form carbon-carbon bonds, which is how you build big molecules from small molecules. However, because the conjugate acid pKa is 25, this is also a fairly strong base. So like the enolate, it can't quite make it over the hump and get an A because it's too strong of a base. Okay, so only nucleophiles above this line, the A's and B nucleophiles, are good enough for an SN2 reaction. Is this an exhaustive list? No, but it gives you an example of the types of molecules that you would expect to see that are capable of acting as nucleophiles. Below the line now are the C's. These are all nucleophiles because by definition a nucleophile is something that has a lone pair. I wouldn't be able to give something an F unless it didn't have a lone pair at all. But F minus is going to get a C. It's not a good enough nucleophile for SN2 because of its extreme electronegativity. Fluorine is the most electronegative element and it just doesn't like to share. That's all there is to it. And then we get into neutral molecules in which the nucleophilic atom is an oxygen, so water and alcohols. They can be nucleophiles. As we will see, these are good enough nucleophiles for SN1 reactions, but they're not good enough nucleophiles for SN2 reactions. Okay? Because The oxygen atom is too electronegative to really want to be able to share those electrons, and you don't have the minus charge destabilizing these things enough to make them really want to react. Water and alcohols are really kind of happy just sitting there as they are. That's why we've got so much of them around. And then finally, I could also add to the C, or maybe I should have made these D nucleophiles. There are other functional groups like ethers, esters, aldehydes, ketones, amides, etc., that have oxygen or nitrogen atoms on them that have lone pairs. It's just in all of those cases, you either can't eventually make something neutral at the end of the mechanism, as we shall see in a later slide, or they're just too electronegative or too weakly basic, too weakly nucleophilic. Those lone pairs are too happy with where they are to be able to participate as nucleophiles in reactions. Okay, so take-home message, the A and B nucleophiles, weak bases, not very electronegative elements, larger atoms, those are the ones that are going to be the best nucleophiles, and the A's and B's are the ones that are good enough to be nucleophiles in an SN2 reaction.